Alright, so in this video, we're going to continue our discussion about mini electron atoms, right? Talked about the Oppenheimer approximation in the other video, and so we're going to build from there. Okay. So we've settled that the nuclei are at fixed locations, right? And now we're trying to solve for the wave function of the electrons, right? We have the Schrödinger equation for the hydrogen atom presented here on this slide, right? And this is what we solved to find the things for the hydrogen atom, right? We have the kinetic energy terms, right? There's the kind of the r distance kinetic energy, the rotational kinetic energy, right? The first two terms, and then the third term is that potential Coulomb attraction between the nuclei and the proton, or and the electron, right? Nuclei and electron. Okay. So, but when we have more than one electron, there's an extra term that needs to be added in, another potential energy term. And this potential energy term is the electron-electron repulsion between these two electrons, okay? And so the electron-electron repulsion, right, as the same type of Coulomb interaction, right? It's the charge divided by the separation distance, okay? And so my separation distance here is Rij, is what I'm calling it. It's the distance between electron 1 and electron I and electron J, right? Which, you know, is something, right, where Rij would be something like Ri minus Rj, okay? So Rij is just essentially the difference, right, between, you know, the position of electron I and the position of electron J, right? Now the problem is that this, right, term here, the fact that I'm dividing by this, right, the fact that I have 1 over Rij makes this a problem, okay? Right, and it's a problem because, right, when we solve this, right, Schrödinger equation for the hydrogen atom, right, so for the hydrogen atom, we do not have this last term here, right, this not for H atom, right, it's not here for the H atom, right, this is only when you have multiple electrons, this is your electron-electron repulsion. Right, your electron-electron repulsion, right? So that term doesn't exist for the hydrogen atom, and because of it not existing, we're able to separate variables, solve 3 different one-dimensional differential equations, and go about our merry way, right? But for multi-electron atoms, I cannot separate my variables anymore, okay? Because of this 1 over the separation distance, okay, there's no way I can somehow take 1 over Rij and set that equal to some function of Ri plus some function of Rj, okay? This cannot happen, right? There's no way you can do that without doing some type of an approximation, okay? There's no exact method to do this, so I can't separate my variables. So this is a differential equation we cannot solve, okay? And so this is true for any atom or molecule that has more than 1 electron, right? Kind of a bummer, because most everything has more than 1 electron, right? And so we have to use some type of approximation, right, for our wave function, for our system, in order to solve this, right? And so the approximation that's typically done for many electron systems is that we assume our wave functions look kind of like hydrogen atom wave functions, right? The orbitals look like s and p and d orbitals and things like that they would for 1 electron systems, okay, right? And then that our total wave function is just a product of these 1 electron wave functions, okay, right? So again, right, I can't actually separate variables without making some kind of an approximation, right? And we're basically just going to make that approximation. We're going to say we can't separate the variables for our wave function. The Hamiltonian can't be separated, right? That Hamiltonian can't be separated, but I'm going to say the wave function can be separated into single electron wave functions, right? This total wave function we have here is separated into a wave function for electron 1 and a wave function for electron 2, Okay, and so that is the approximation that's typically made for many electron systems, is that we have that type of assumption for the wave function, and then that's done on top of the Born-Oppenheimer approximation. Okay, and we'll kind of discuss some of these things a little bit more detail later in terms of electronic structure theory, independent particle approximation, and things like that, but we won't cover that today. Right. And so we'll talk a little bit about what I had mentioned previously in kind of the electron spin video, okay, which is this Pauli exclusion principle or Pauli principle, right? And this has to do with the fact, again, that the electrons are indistinguishable particles, that they're fermions, half-integer spins, okay? And so, right, for some indistinguishable particle, right, I have a wave function where I have R1, theta 1, phi 1, right, and then R2, theta 2, phi 2, right, right, and then in this case, I've just now changed my labels, right, I've just decided to call, right, R1 is now being called R2, R2 is now being called R1, right, I've just changed the labels for the wave function, right, and for fermions, for electrons, right, that wave function, right, needs to be anti-symmetric, right? So that I need to have a wave function here that is anti-symmetric, right? So that they equal each other, but with opposite sign. So anti-symmetric exchange, right, means that I have this multiplied by -1 term, okay? And this is the Pauli principle, which leads to the Pauli exclusion principle, okay? The fact that my wave function has to be anti-symmetric when I exchange the labels of two electrons, because again, right, I can't actually distinguish between two different electrons, so calling one electron 1 and the other electron 2 is very arbitrary. And so exchanging those arbitrary labels for fermions means that my wave function has to be minus that of itself, okay? In this Pauli principle, this principle for fermions, okay, leads to the Pauli exclusion principle that no two electrons can have the same quantum numbers, they can't occupy the same space with the same spin. Okay, so kind of click a question to kind of review some of the things that we've talked about in this video, and the last, right, so which of the following makes it impossible to separate variables and to solve the helium atom exactly? Is it the nuclear kinetic energy, the electron kinetic energy, the nuclear electron attractions, or the electron-electron repulsions? Okay? And the only one of these terms that I can't separate into, one variable quantities is going to be D here, the electron-electron repulsion. Okay? Electron-electron repulsion is the only term that's making it so I can't solve this exactly, right? The electron-nuclear attraction terms, right? The nucleus are stationary. I'm not solving for the nuclear wave function, so those are just some point charges in space, right? And so those, I can separate each one of those into different one-electron terms, okay, and fully separate my variables, okay? Same with the electron kinetic energy, nuclear kinetic energy. Those can be fully separated, but the electron-electron repulsion cannot. All right. So often we talk about many electron atoms and molecules in terms of their electron configuration. Okay, the electron configuration, right, is just describing what orbitals electrons are occupying, right? So, right, we'll give different MO diagrams, right, but we can talk about, right, the 1s orbital, 2s orbital, right, the 2p orbital, so on and so forth, right? The electron configuration is saying, right, that I have right, these number of electrons, right? This is, say, the electron configuration for 1, 2, 3, 4, 5, 6, 7, right? So the nitrogen atom, right? This is for the nitrogen atom, right? So there's a nitrogen. Another way to write that electron configuration, right, is, remember from general chemistry, 1s2, 2s2, 2p3, right? This would be the electron configuration for nitrogen. And so whenever we're talking about electron configurations, whenever we're using that term, it's just saying, you know, what is the set of orbitals that the electrons happen to be occupying? And that is the electron configuration. Okay. All right. And, right, so let's erase this here just so you can kind of see what's on the slide, right? This is just kind of stating what I was just writing out and what I was just showing, right? That the say, electron configuration for neon is given as such, right? And resonance structures, as you learned about in organic chemistry, right? The idea of those is just that you have some molecule that has multiple electron configurations that make up what the actual wave function might look like, okay? Right, resonance structure for benzene, for example, right? You have this, and then, that was much worse benzene here, right? You have these two like resonance structures for benzene, okay, right? And each one of these resonance structures describing a different set of electron configurations in terms of the electrons occupying certain p orbitals versus other p orbitals, right? And so electron configurations will follow certain rules, right? First is the Pauli exclusion principle, right? That you can't have, right, two electrons with the same quantum numbers, meaning you can't have more than two electrons in a given orbital, right? Right? And so, right, if two electrons occupy the same orbital, they have to have opposite spins. That's related to the Pauli exclusion principle. And then there's Hund's rule, right? And Hund's rule is just stating, right, that the if, right, for the p orbitals that I drew in the previous slide, right, the two p orbitals, right, that my electrons are going to first unpair like this, okay, before pairing up in orbitals. That this is lower in energy, right? This is lower in energy than if I had something like this, where I paired up two of my electrons instead of leaving them all unpaired. Okay? And we'll when we get to the independent particle approximation in later videos, right, later in class, right, we'll kind of see why this is the case, where this comes from, okay? But so this Hund's rule is based off of kind of what's called exchange interaction between electrons and things like that we'll get to eventually, okay? But it's based off of actual things that are going on. It's not just some empirical observation. There is a reason why electrons want to first singly occupy orbitals before doubly occupying the orbitals. Okay. Right. And so then finally, just kind of talking a little bit more about electron configurations and occupying orbitals, right? Right, there's things, right, we talked about for the hydrogen atom, right, if we assume just a hydrogen atom, right, the energy of the n equals 3 levels are always less than the energy of n equals 4 levels, right? It's always true, right, it's always lower in energy. I shouldn't, like, less is kind of misleading, right? It's always lower in energy, right, it's more negative, right? The electrons want to be at lower and lower energy, which is more and more negative, okay? So it's always lower in energy, okay? And so you would expect to fill up the 3d orbitals before the 4s orbitals, but that's not the case, okay? Right? You know, your transition metals, right, are not filled up in that way, okay? And the reason for that is because these 3d orbitals their average distance of electrons in 3d orbitals are closer to the nuclei than they are in the 4s orbitals, okay? And so while they're closer to the nuclei and that potentially stabilizes them, they're also closer together, meaning that the electrons within those 3d orbitals feel more electron-electron repulsion, right? So that then they are, you know, that's going to make them be at a higher energy, right? So you have this kind of competing terms of 3d orbitals in which they are closer to the nucleus, they are potentially lower in energy because of this Coulomb attraction to the nucleus, but then they also are higher in energy, have this energy penalty because they're more compact, meaning that the electrons that occupy those orbitals are repelling each other more strongly, which is not a favorable thing, right? And this is part of the reason why, for example, when you ionize certain transition metals, you remove electrons from certain d orbitals versus s orbitals and other things like that, right? So, right, when we talk about transition metals, what the exact electron configuration can be a lot more complicated than simply thinking of things just as a hydrogen atom. So you have to think about electron-electron repulsion and other things like that. And again, we talk about the independent particle approximation and other things later in class, right? We'll kind of get back to kind of seeing and understanding why that is the case.